Yeah, like Rob said, Johan Ervenius, systems engineer at Arista Networks for 8 years now. And today I'm going to talk about an initiative called Ultra Ethernet, which is an initiative within networking for AI, which started about 2 years ago. And the first version of the specification for Ultra Ethernet was released in July earlier this year. And is this supposed to work? Well, it doesn't. The clicker doesn't work. Oh, there we go. If you purchased equipment for an AI cluster, I mean, you probably spent a lot of money, right? And even if you haven't, I guess you can imagine that it costs billions or millions or billions of dollars, right? And of course, you want to get a good return on investment by having that cluster perform efficiently. And the single most important metric, and I think you've heard this before today, to sort of measure that efficiency is the job completion time. And somewhat simplified, there we go. Somewhat simplified, that job completion time consists of first the GPUs, sort of crunching data, doing the actual job, and then the GPUs sharing the results among themselves, sort of over the network, right, which is called the time spent in networking. And I mean, we've seen bad network designs where this time spent in networking could easily sort of be up to 50% of the total job completion time, and that is really not getting good value for money for the very, very expensive GPUs. So, what is it that differs between sort of an AI network, a back-end AI network, and a normal DC for generic compute, right? Well, first of all, endpoints are fast. 400 gig, 800 gig. Load is high. And when the GPUs send data, they do so all at once and at full speed. So there are flows with very, very high bandwidth. Elephant flows, someone else mentioned earlier today. But the number of flows is actually quite few compared to a normal data center. And the round trip times are extremely short, microsecond from end to end. And the issue with that, with having few flows with high bandwidth, is that you easily get congestion, right? And congestion leads to poor network performance. And the thing is with AI flows is that the completion time, this time spent in networking, is really determined by your slowest flow. And I'm going to come back to that because that's important. But bottom line is that your vanilla DC networking doesn't really meet the needs for this. And to address this issue, there was a joint development foundation project called the Ultra Ethernet Consortium, founded about 2 years ago. The 10 founding members, as you can see, a number of network vendors, chip vendors, some of the hyperscalers and so forth, they sort of founded this, and it has now grown to over 100 active member companies. And the mission that the Ultra Ethernet Consortium has is to deliver a full architecture for Ethernet, optimizing Ethernet for AI and HPC networks. And the focus is really on functionality, performance, total cost of ownership, development and end user friendliness, but at all times sort of keeping Ethernet interoperability sort of the main point here. And as most standard organizations, you have multiple working groups working sort of all different layers of the stack on cross-layer functions and so forth. As I said, I mean, this work has now resulted in the 1.0 version of the specification for Ultra Ethernet, and it really consists of functions for all of these different layers. But I believe that the most important work has been done by the transport working group that has resulted in the Ultra Ethernet transport protocol, which I will sort of focus on in this presentation. Let's go sort of back to some basics here, what is important in an AI network, right? When GPUs communicate, they do so using a concept called remote memory access. And that is memory on both on the sender side and on the receiver side communicating directly, sort of bypassing the kernel of the hosts where they're located, right? And this is to minimize latency and to maximize throughput. Our DMA, remote direct memory access, is an implementation of the RMA concept, right? And it's widely deployed, and it has functionality for sort of loss detection, for recovery, and so forth. And it can actually run over Ethernet and IP, which is RoCE, RDMA over Converged Ethernet version 2. So, I mean, the concept of RMA, that's not going to change, right? Direct memory access or memory communication from between source and destination. RDMA was initially sort of made popular with InfiniBand, as you sort of might know, right? But what the UEC believes is that Ethernet is really the right foundation for RMA going forward. And the reasons for that are simple. First of all, we have a broad ecosystem within sort of the Ethernet community with multiple vendors at different layers, right? There's multiple tools for operations, for management, for testing, and so forth. And it scales. I mean, the internet is built on Ethernet and IP, right? And given it's like 50 plus years of sort of being the network protocol of choice, it's really, really well understood. So, I mean, for the UEC, there was no option. I mean, this needs to build on Ethernet going forward. Okay, so Ethernet it is, right? But I mean, we already have this RDMA, remote direct memory access, right, running over Ethernet. But one issue with RoCE is that it requires that flows or that packets belongs to a flow follow the same path through the network. I mean, they can't be out of order packet delivery, right? So another sort of drawback of RDMA is the recovery mechanism. So even if you only lose one packet, you typically have to go back sort of to the beginning of a sequence and resend multiple packets just because you lost one packet in the network. Another sort of thing that is problematic is congestion control within RoCE. It's rather hard to tune, and it doesn't really interrupt very well between different sort of NIC vendors and so forth. And with the sort of increasing scale requirements, and there's also requirements for sort of built-in security into this, there's really a need for a new protocol. Before going into that protocol, let's talk about the sort of main problem to solve, right? And that problem is load balancing. With bad load balancing in your network, you're going to get congestion, and congestion leads to sort of flows slowing down. And if you remember from the beginning, the slowest flow is what really determines this time spent in networking. If you look at sort of a normal UDP or TCP stream today, right, typically how that works through a network is that they have to follow the same path. And the simple reason for that is that those protocols, they don't like to receive packets out of order. If packets arrive out of order, that's typically interpreted as loss, and repeated loss is interpreted as congestion, and then the sort of flows, they slow down. And which is going to increase that sort of time spent in networking, right? So the bottom line is that with these legacy transport protocols, you can't reorder your packets, which means you have to follow the same path through the network. And that makes it hard to load balance. If we look at basic sort of load balancing sort of theory, right? When a flow arrives at a switch and there's multiple paths to the destination for that flow, for a switch, the switch has to sort of make a hash of the flow information in order to sort of choose one of the outgoing interfaces. And typically it chooses the layer 4 protocol. You have source destination IP, source destination layer 4 port. And it creates a hash, which in turn sort of at the end makes the switch select one of the outgoing interfaces. And this works great in a normal data center where you have thousands or tens of thousands of different flows, right? That's not that big. It's going to get a fairly even load balancing through the network. But it doesn't work well at all, or it's hard to do when your flows are big and few. So if we look at how good flow hashing actually is, right? We have a few sort of simplified simulations here. So let's assume we have a non-oversubscribed networks. We have switches with like 32 100 gig interface downstreams and 32 100 gig interfaces upstream. So a completely non-oversubscribed networks. And we have 32 servers here. They're sending, they connected at 100 gig. They're sending 80 flows each at 1 gigabit. So a lot of flows that are not that big, right? And if we look at the graph here, I mean, you can basically see everything on the right side of the green line there is the links that are actually getting more flows than what they can actually carry, right? But it's not that many, right? So your average throughput is pretty good. So this is the scenario typically for a normal data center. If we, instead of sending 80 flows of 1 gig, we send 8 flows of 10 gigs, so more like an AI type of traffic scenario, right? Suddenly we're going to get a lot more congestion. There's going to be a lot more links in the network that has to carry more traffic than what their capacity actually is. Still, I mean, your average throughput is, I don't know, 97%, so still pretty good. But if you remember again from the beginning, the problem with the traffic spent in networking is not that it's determined by your average throughput, it's determined by the slowest flows. So, and the reason for that is, I mean, the way it works is that all the GPUs, they have to sort of share the data among themselves before the next job cycle can sort of continue or begin. So if you look at the worst case scenario, your typical worst case scenario will have links carrying 1.4 times their capacity. And that's going to cause major congestion, and suddenly you're going to get down to something like 70% throughput in your worst case, which is simply not acceptable, right? You're going to get a lot of congestion. Your time spent in networking is just going to go up. There's a lot of band-aids that has been sort of done, or a lot of advanced load balancing functions to sort of battle this, right? We heard our favorite competitor earlier today talk about using SRv6, for example, to program flows through the network. There are load balancing algorithms that can also look at the link utilization, so dynamic load balancing, before choosing which link to sort of send out traffic on. But I mean, again, all of those are really, really band-aids. It doesn't really address the underlying problem, which is that a single flow has to follow the same path through the network. So what if we forget about keeping packets in order? What if all packets belonging to a flow could actually use all paths? So again, same scenario, right? But instead of having these 32 servers sending 8 flows, they instead packet spray all of those sort of 80 gig of traffic in 204 different ways. So basically packets with 204 different types of entropy that the switch can then use to sort of hash through the network. And suddenly, in your worst case scenario, you actually get only 91% sort of link utilization on your worst congested links. And that's even below the sort of capacity of a link, right? So suddenly, your worst case scenario, you have 99.98% utilization. So packet spraying is really, or sort of not having packet following the same path of the same flow, following the same path in the network is really sort of the way going forward. The problem, though, this doesn't work with TCP and vanilla RDMA. Those transport protocols really require that you follow the same paths, because otherwise your packets will arrive out of order. So this brings us to the Ultra Ethernet Transport Protocol. And what that is that it's an advanced remote memory access protocol that has 2 major functions. It has relaxed packet ordering, and it has support for packet spraying. And the way it supports the relaxed delivery ordering is that it's tagging each packet with its final destination in memory, right? So it doesn't matter in which order they arrive. Every packet knows exactly into sort of where into memory to go, right? So if you look at sort of older RDMA implementations, typically the destination was sort of relative to some earlier packet in the same flow, right? So if you lose some packets, it's hard to sort of place them into the correct place in memory. But here, every packet is tagged with its final destination. And that sort of relaxed delivery ordering makes it then possible to packet spray packets over the network. And as we saw, I mean, that's really going to help balance the load across the network. However, there are of course some challenges with spraying packets over the network, right? And one of them is loss detection. With a traditional sort of transport protocol like TCP, I mean, the way you discover loss is that packets suddenly arrive out of order, right? Then you know that you've lost a packet somewhere along the way. So obviously you can't use that if out of order packets are allowed. Another issue is that these networks are extremely fast. I mean, if you want to send, I don't know, 1 megabyte of data, that's going to take like 10 microseconds at 800 gigs. You can't have any kind of timeout waiting for a packet to arrive and then discovering, oh, it's not going to arrive, then it's actually lost, right? So you can't use timeouts in any way. And what is also desirable is that you only resend packets that you lose, right? Not sort of an entire sequence just because you lose one packet. And the way that the Ultra Ethernet Transport Protocol solves this is by something called packet trimming. So basically what happens is that when a packet arrives at a switch and the output queue is full, in a normal case that packet would just be dropped, right? But what the switch does in this case is that it actually truncates the packet down to 64 bytes. So if it was a 9K or a 4K packet, it goes down, I don't know, 99% in size. It also takes the DHCP field of the IP header and sets that to a value that you have that has the meaning that it's actually been trimmed, so that the receiver knows that this packet has actually been trimmed. And what it then does is that it actually puts this packet into a high priority queue. So it actually gets sent out of that switch, out of that interface much, much faster than if it would have been queued in the normal sort of output queue, right? So this packet is going to arrive at the receiver much, much quicker than some of the packets that were actually sent before it, but that are now stuck in a queue. And the receiver, when it gets this packet, they see, okay, this is a trimmed packet, so it was actually lost. I mean, all the payload is gone, of course, right? So it has to be resent. So the receiver sends a NAC back to the sender that then sends a new copy of that packet. And the beauty here is that the sender can now change the entropy of that packet, so it potentially actually takes another path through the network, sort of avoiding this congested queue. So it's really a switch support for really, really fast loss detection. Okay, so now that we have packet spraying, right, we need to have also methods for congestion control. And again, if you look at traditional transport protocols like TCP, the way that works is that they typically start off slow, right, before blasting the network at line rate. So they can discover if there is congestion somewhere in the network before sort of sending at full speed. And if congestion is discovered, they're going to slow down and then start again. I mean, the typical TCP sawtooth pattern. But I mean, with the round trip times that we have in AI networks, that's not possible. I mean, if these 10 microseconds that I had as an example, we have a sort of a slow start to that. That's easily going to take 20, 30 microseconds. You're doubling or even tripling your time spent in networking, and that's not really possible. So there's really no way of sort of having any kind of slow start. So you really have to have you have to basically start at line rate for every flow, and then really have algorithms to do a fast back off if you discover congestion. So you need algorithms to quickly ramp up, quickly slow down if congestion is sort of detected. And it, of course, also must work with this packet spraying technique that I talked about earlier. The default congestion control mechanisms within the Ultra Ethernet Transport Protocol is called Network Signal Congestion Control, or NSCC. And this is all sort of done from the sender NIC. And it really enables sort of fast ramp up and fast slow down. And it works with 3 different signals. First, it measures the round trip time for a packet. So it measures the latency from when it actually sends a packet until it receives an ACK for that packet. And the good thing about that is it's really granular, because I mean, different packets will obviously have different latency through the network. Some might get queued for a bit and some doesn't get queued and so forth. So it can really adjust the entropy for some of the packets. If it discovers that packet sent when this specific entropy actually has a higher latency than everyone else, it can adjust that entropy and sort of smooth out the sort of latency for all the packets, so it gets a good average latency for all the packets through the network. It also uses ECN bits, just like how it works in sort of normal IP networks, which is, of course, a bit that a switch would send if a packets get enqueued for a certain amount of time. And it also uses this trimming functionality that I talked about, because that actually indicates that there are drops in the network, which is, of course, a congestion scenario. So somehow you have algorithms that efficiently use a combination of all of these three different things to really have a really efficient congestion control mechanism. Another optional congestion control is on the receiver side, and that's really for optimized for handling in cost, which is sort of many talking to one and creating congestion scenario in that sense. And the way that this works is that the receiver is actually sending credits to the sender, kind of how like virtual output queuing works in a networking ASIC, right? And this really works along the default sender-based congestion control. When you talk about a new protocol, you of course must have a picture of the actual packet frame. And if we start at the bottom right, we have the standard Ethernet and IP headers. And this is the whole point of Ultra Ethernet, right? It needs to work on top of what's already out there, what's already working. On top of that, there's a UDP header. The UDP header is actually optional, and the only use case for the UDP header is to create the entropy, so different sort of UDP ports in order to make the switch sort of hash the different packets in different ways. There is, as you can see, an entropy header at the beginning of the UET header, but the thing is that in the IP header, you have a field for indicating the next protocol that comes after IP, right? And there hasn't yet been a number assigned to Ultra Ethernet, so you need to have a known protocol sort of in between, and in this case it's UDP. Once that number gets defined, you can actually remove the UDP header and use the entropy header instead, or entropy field in the UET header. There are two main fields in the UET header. You have the PDS, the packet delivery sublayer, and that's really responsible for all the functions that I've talked about, the sort of congestion control, the packet spraying, and all of that. And then you have the SES, the semantics sublayer, where really maps sort of the payload to the actual packet, so the RMA functionality, setting the correct sort of RMA destination address into memory and so forth. Another header that is optional is called the transport security sublayer, because security is really first-class citizen within the Ultra Ethernet transport, which makes it possible to encrypt the entire payload and part of the UET header as well. And then at the end, you have a sort of normal CRC trailer, which is also optional, and also a trailer for the security part. And as I said, there's multiple working groups within the Ultra Ethernet Consortium working on different things. The transport protocol is probably the most important part, but the specification includes some other things as well. And jacking in sort of to the transport layer from above is the API called libfabric 2.0, which is a modern API that has been developed by the Open Fabrics Alliance. So this is a widely used API actually for HPC and AI applications. So this is not something that the UEC has done. They have selected this API as being part of the sort of Ultra Ethernet stack. And the reason for using this instead of normal sockets API is that those sockets aren't really rich enough for the functionality required for HPC and AI networks. If we go sort of below the transport header, we find at the link layer the link layer retransmission functionality, because I mean that packet trimming thing that enables sort of an end-to-end retransmission on packets if they get lost, right? But I mean in huge AI networks you have thousands or even tens or 100,000s of links, so you're going to have issues sort of on links on sort of a regular basis. And of course it's much more efficient to resend the packet on a specific link than sort of course from end to end. So the way that this works is that first of all the feature is negotiated with LLDP, so both sort of the sender side and the receiving side of a link must sort of support this. And the way it works is that the sender actually stores the packet until it has received an ACK for that packet, And if it receives a knack because the packet was somehow corrupted, it's going to resend it again. So this is really a hardware-dependent feature. It needs to be part of the pipeline of an ASIC, and I don't think there are any ASICs yet that can actually do this. But it's part of the specification, and we'll probably see this in the future. Work does, of course, not stop after the 1.0 specification. There's work ongoing on multiple different things. For example, an API for storage. There's sort of working on for management, debugging, testing, telemetry, and much, much more. So there's a lot of stuff ongoing, and I'm sure we'll see a 1.something or a 2.0 quite soon. But in conclusion, right, the UEC really believes that Ethernet is the standard solution for AI and HPC going forward. And som sagt, the sort of main reason for that is the broad ecosystems out there, right, with all the vendor support and so forth. And it scales, of course. So Ultra Ethernet is now ready for AI and HPC networks of the future. And with that, I thank you for listening.
Thanks, Johan. We have a couple of minutes if there are any questions for Johan. It's difficult to see anything from the balcony, Menti, no? Okay, well, please join me in thanking Johan for a great presentation. Thank you so much.
Thank you.